Hello, this is question 3 on your mechanics paper from Edexcel, November 2021, and you have a beam AB, has mass M, length 2A, is this one here, rest in equilibrium with A on a rough horizontal ground and B against a smooth vertical wall. The beam is inclined to the horizontal at an angle alpha, and the coefficient of friction is mu. The beam is modeled as uniform, resting in a vertical plane that is perpendicular to the wall. If it's uniform, remember we are going to consider the center of mass in the midpoint, so we are going to draw the weight here. Using the model, show that mu it must be greater or equal than 1/2 cot theta. So first of all, with this question, I really recommend you to draw all the forces. So we have the weight pointing down, the mass of the rod is m, so it's going to be mg. In this wall, we don't have friction, but we have normal reaction. Normal reaction is always perpendicular to the surface, not to the rod. So it's going to be perpendicular to the wall. And I'm going to call it RB. Then here we have the same perpendicular to the floor, normal reaction, and then we have a friction. It's not moving, so sometimes it's difficult to think where in the direction of the friction, but just think how this could move if you don't have friction. So if this was very slippery, the ladder or the rod will slip this way. That means that the friction is the other way. Yeah, so the friction is pointing against the wall. I'm going to call it FR. We know that friction, just to find we need to find mu. Every time we need to find mu, we need to use the same equation. So friction is always smaller or equal than the maximum value, which is mu normal reaction. Yeah, that means that mu, making mu the subject, mu must be greater or equal than friction divided by RA. So what we are going to do is to find friction and RA and dividing to see what mu must be greater than. It's in equilibrium, so we can apply two things. Or sum of forces, resultant force in any direction is 0, or moment about any point is 0. And in all the questions we will need a combination of both, yeah? So if we apply, so we need RA, and RA is quite straightforward because if we resolve vertically, we only have two forces. So RA pointing up is going to be equal to mg pointing down. So resolving vertically, we have RA pointing up equal to mg pointing down. So we have one of the two things that we need. And now to find the friction, if we solve horizontally, the friction is going to be RB, but we don't know RB either. So we're going to take moments. We can take moments about this point, for example, and we will have three forces in our equation, or we could take moments about this point and have only two. If we take moments about this point, we won't have friction in the equation, but we know that friction is going to be RB. So we can find RB and straight away say that that's the friction. And I think that's simpler, but you can take moments about B and you will get the same answer, yeah? I just think the least forces in your equation, the simpler it is. So if we take moments about A, we have that must be 0, so clockwise moment equal to the anti-clockwise. About A, this one is producing a clockwise moment, yeah? This is rotating around A clockwise, and this one in the direction of the force is anti-clockwise. So this one is anti-clock. So one must be equal to each other. The moment of this force is going to be the force times perpendicular distance from the point to the line of the force, yeah? So if this is the line of the force is acting in this line, we are looking at this distance here. If you look at this right angle triangle, this is A, because the whole rod is 2A, so this is A, angle adjacent. That means that this distance is going to be A cos, because it's adjacent. So I have mg times A cos theta. That's going to be equal to the anti-clockwise. This force and the perpendicular distance from the point to the line of the force. So we are talking about this distance. This distance is exactly the same as this one. And we have this right angle triangle. This is 2a, and this is the opposite. So it's going to be 2a sine theta. So the force, RB, times 2a sine theta. And from here I can find RB. So I can cancel A, for example, and RB is going to be mg divided by 2 cos theta divided by sine theta, which is mg, and I'm writing cot because we have to find, to show that is cot, yeah? This is RB, and we know that RB is equal to the friction, yeah? Resolving horizontally, we are using everything that we can use. Resolving horizontally, so force pointing right or force pointing left, which is RB, is equal to friction. So that means the friction is what we just found, cot theta. Therefore, mu must be greater or equal than, just substituting here, friction, which is mg cot, so mg divided by 2 cot theta, divided by RA, that was mg. We cancel mg, and we have that mu must be greater or equal than 1/2 cot theta. And that's what we needed to prove. Yeah, that's the first part. Then for the second part, a horizontal force of magnitude kmg, where k is constant, is now applied to the beam at A, acts in the direction that is perpendicular to the wall and towards the wall, and we have tan, we have mu, and now is in limiting equilibrium. So this means, remember, that the friction is going to be maximum, so friction is going to be mu normal reaction, and use the model to find the value of k. So we have to think what happens with the other forces when we apply one force. So we are applying one force perpendicular to the wall in this direction, that is kmg. So we have to rethink about the friction. So if I am applying a force that way and it's in limiting equilibrium, that means the friction, so that means it's about to move that way, in that direction, which means the friction is the other direction, is opposing to the motion, yeah? So we have to change the direction of the friction. Be careful, because that happens in many questions when you add a force or remove a force. I need to find this k. So what we can do is to solve horizontally. If we solve horizontally, we have this force in terms of friction and this normal reaction. I can find easily the friction because I have mu and I have normal reaction. This hasn't changed, yeah? What I need to find is, that's it, I have the friction and I have the normal reaction. I need to find RB. So let me show you. If we, for B, if we resolve horizontally, we have that RB pointing left plus the friction pointing left is going to be equal to this kmg. Yeah? Friction, as is in limiting equilibrium, is going to be mu normal reaction. This is kmg. Mu is 0.5, normal reaction, this is the normal reaction at A, is still mg, like it was before, it hasn't changed, yeah? What happens with RB? RB, if we take moments again about A, we have the same situation that we had before, yeah? So mg hasn't changed, moments about A must be 0, so RB hasn't changed. It's not always the case, so be careful, but RB hasn't changed. So RB was this function here. So substituting RB, I have mg divided by 2 cot theta plus mu that we know is 0.5 RA, which is mg, is going to be kmg. We can cancel mg everywhere, and we can substitute cot theta by the value that it has, because tan is 5/4, that means cot is 4/5. Yeah, it's the reciprocal, 4/5. So I have 1/2 times 4/5 plus 1/2 equal to k. Therefore, just adding those values, k is going to be 9/10 or 0.9. Yeah, and that's the value of k. And that's all with this question. That's the last thing they ask you, the value of k. Yeah, that's all.